Now we're going to talk about functions in polar coordinates, and we're going to draw some pictures. So this is going to be mainly just an introductory section to show you what these pictures look like and how to convert formats from polar version back to rectangular and so on and so forth when you're talking about functions that have polar coordinates involved. So just as I said a minute ago, recall, so I'll just write it down here, recall, this is basic stuff, what I'm going to say here, that you have y is equal to f of x, which is just some function when you have a rectangular coordinates, okay? And that function is a function of x, and that function, you know, can do whatever. It just looks like this, and you take a value of x in, you put it into the function, you get a value of y back, and you plot it. That's what a function is, okay? So in polar coordinates, okay, in polar coordinates, we write functions like this. We write functions as following. Instead of f of x, okay, y is equal to f of x, we say that r is equal to some function of theta. Okay, so you see the analogy is direct here. Instead of y, the other coordinate being a function of x, we say that r, which is one of the coordinates in the polar representation, is a function of the other coordinate, theta. Okay, so basically you have remember what r is. It is the distance from the origin, and the angle is just the angle measured from the x-axis. So the distance from the origin is a function of the angle as you go around the xy plane here. So you're going to trace out some sort of pattern as you trace your angles out. R is going to change, and you're going to get some cute little figures. A lot of times they have circular symmetry, but not always. Okay, so let's look at an example. What would a real polar equation look like? Okay, let's look at the polar equation of a circle, because that's one that you're gonna see over and over again, because one of the nice things about using polar coordinates to begin with is that they're nice when you apply them to circular problems, things that involve a circle. Okay, the polar equation for a circle is, drum roll please, r is equal to, for instance, 2. This is an example. R is equal to 2. This is it, ladies and gentlemen. That is the equation of a circle. It's extremely simple. You see what's going on here, okay? Let's go ahead and look at this and just see if we understand what's going on here, okay? Now, notice I said that in general, r is a function of theta. I did say that. So in general, what I'm saying is that r, as you start here and as you trace out theta, as you go all the way around the xy plane like this, okay, r is going to change. It's going to be a function of theta. As you sweep theta, r might be this big, and as you increase theta, r might get bigger and smaller and bigger and smaller, and you trace out a function, right? Well, this very, very simple function means, see, there's no theta over here at all. It's not even here. That means that, yes, in general, r is a function of theta, but for this particular function, r is a constant. R doesn't even change. No matter what value of theta you pick, because there's no theta in the equation, r never changes. So what you basically have here is, and that's why it is a circle, because if you start here over here at theta is equal to 0, as you make your way over to theta is pi over 2 and pi and 3 pi over 2 and then back over to 2 pi, you see r stays the same. It's a function of theta, but it's just that it doesn't change, you see. So that is why that's why it's an equation of a circle. And look at how simple this relation is, this function is. It's very, very simple, and that's because it has circular symmetry, and that's what I was telling you before. Polar equations are really, really useful for circular symmetry. Now, notice that I'm going to change colors here. Notice that the rectangular form of a circle, just to refresh your memory, the rectangular, when I say rectangular, I mean the Cartesian coordinate version of a circle with radius 2 is x squared plus y squared is equal to r squared. So in this case, it'd be x squared plus y squared is equal to 4, because the radius is 2 here, so you square it and make it 4. Now this is the equation in rectangular coordinates. This is what you've learned all your life, is the equation of a circle centered at the origin, right? So this, if you're going to plot this or work with this, is kind of ugly, because if you try to solve for y, if you want to plot this thing, you've got to move x squared over here and take the square root, so you're going to have square root of 4 minus x squared. there, and then you're going to have that thing under a radical, and it's plus or minus, so you have one function that traces out the top part and one function that traces out the bottom part. So you see, it's just not very simple to work with. You start taking derivatives of this thing. If you solve for y and start trying to take a derivative, it's going to be an ugly derivative. It's just not very friendly to work with, and that is simply because you're using a grid, which is what x and y is, a grid system, that's what x and y is, to describe a circle. So it just doesn't lend itself very well to it. We've gotten used to it because this is how you're introduced to it, but it just isn't very, very nice. Now the polar representation, by its very nature, because it's based on angles and radii, okay, it is basically a circular system. So that's why the function of a circle is so simple. And if you start manipulating this, taking derivatives, doing other complicated things with functions this simple, it becomes very, very easy, and that's why it's so useful. And that's why you need to learn it. So let's go on and just look at some examples here. What would be another function in polar coordinate system? What if you had a function that was just simply theta is equal to 3 pi over 4, and you were asked to plot that? What would that one look like? Well, I'm giving you a couple of special cases here in the beginning, and so this is a special case here. Notice again what you're saying here. Let me go ahead and just give you the answer here, and we'll talk about it. What would this thing look like? Okay. Normally we said that it's r is a function of theta, which is true. But in this particular case, what you're saying is that theta is equal to 3 pi over 4. Okay? There's no r in there. There's no really any function of theta. It's not like r changes as a function of theta. What this equation says literally is that forevermore, no matter what happens, theta is equal to 3 pi over 4. So this is a line, and this angle here, let me go ahead and write it in red here. This angle here is 3 pi over 4. So make sure you wrap your brain around that. That means that forevermore, theta is equal to 3 pi over 4, so it's just a line. It's very similar back in algebra when you were learning about the equation, the rectangular equation, y is equal to 2. And you said, well, what does that line look like? Or what does that equation look like? And it's a line that goes like this, because forevermore y is equal to 2. Okay? And likewise, x is equal to negative 3 is a line that looks like this. X is equal to negative 3, right? Because forevermore x is equal to negative 3. It doesn't look like a regular function, but because what it's saying is that coordinate is equal to a value, then it's basically a line and it goes to that point. So this is the same thing. Theta is equal to 3 pi over 4. It's just saying that forevermore, no matter what happens, independent of r or anything else, theta is indeed equal to 3 pi over 4. So that's why it looks like this. Okay, now let's say you were given a polar equation that said r is equal to 2 times the sine of theta. Now here's a more conventional type of thing that's not really a special case. R, which is the radius from the origin, is equal to 2 times the sine of some angle. So as you go around with different values of angles, you're going to plug them in here and you're going to get the distance from the origin at that point. Okay, so that's sort of truly a function of theta there. So how would you do that? You would make a table just like you always do. You have theta, which is your independent variable. Your dependent variable is going to be r, which is equal to 2 times the sine of theta. Okay, so you just pick some representative values and plug them in. So I'm going to pick 0, pi over 4, pi over 2, 3 pi over 4, and pi. So I'm going to pick kind of a half circle. I'm going to look at a half circle going from 0 to pi, and I'm going to see what this thing looks like. Now, for this one, r is equal to 2 times the sine of 0. Sine of 0, remembering back, is just equal to 0, so this one's equal to 0. 0 comma 0. This one, r is equal to 2 times the sine of pi over 4. 2 times the sine of pi over 4. But remember, pi over 4 is equal to the square root of 2 over 2. So with the 2's cancel, you're just going to have square root of 2. Okay, square root of 2. This one is going to be equal to 2 times the sine of pi over 2. Okay, and remember, sine of pi over 2 is just 1, so this one's simply 2. Okay, and r is equal to 2 times the sine of 3 pi over 4. Okay, so now you're over in this quadrant at 3 pi over 4. So that's going to be also same thing, positive square root of 2 over 2. So it's going to be positive square root of 2 over 2, which is equal to square root of 2. Okay, and the final one that we have here is r is equal to 2 times the sine of pi. And you should know that since pi is over here, that's going to basically be equal to 0. So r is equal to 0 for that one. So what would it look like if we were to plot this guy? Well, let's go ahead and do it right up here. Okay, let's say this is my plane. Okay, now at theta is equal to 0, which is right here in the x-axis. Okay, the radius is 0. So actually, there's a point right here at the origin. Now looking here at the angle pi over 4, which is roughly here at 45 degrees, it's going to be square root of 2 from the origin, and we'll just say that that's right here. Square root of 2 is roughly 1.4. We'll just pick that as a point, so it's 1.4 from the origin here at 45 degrees. Now at pi over 2, which is up here, it's equal to 2, right? So this is 1, and this is 2. So there's a point right here. And then over at 3 pi over 4, which is over here, you're also at square root of 2, which is the radius from the origin, which we're going to say is roughly right around there. And then over at pi, by the time you make your way back over here, you've come right on back into 0. So you see what this thing looks like? It looks like a circle. It's sitting right up on top of the axis like that, okay? And if you were to, plot that circle in Cartesian coordinates, it would look a whole lot more complicated than 2 times the sine of theta. That's just a pretty simple looking expression. And that's, again, why these things are useful. Okay, now the next one is, what if you were given a function r is equal to theta? R is equal to theta. What would that thing look like? Well, you make yourself a table. Again, it's going to be a pretty simple table this time. R is the independent variable, and r is equal to theta is my dependent variable. Let's pick some values. 0, pi over 4, pi over 2, 3 pi over 4, and let's say pi. Those are my favorite values there to split it up. And let's go ahead and say 5 pi over 4. So we're just basically picking some angles going around the circle like this. And since r is equal to theta, these values are exactly the same. Pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4. And these values here are the radius, or the distance from the origin there, okay? So if we tried to plot something like this, what do you think it would look like? Okay, at the angle of 0, which is right here, the radius is 0, so you have a point right here in the origin, okay? At pi over 4, which is 45 degrees, you're pi over 4 away, so we'll say pi over 4 is, let's just say roughly there, okay? At pi over 2, an angle of pi over 2, you're pi over 4 away from the origin, which is farther than pi over 2, so let's say you're roughly there, okay? At 3 pi over 4, which is over here, you're 3 pi over 4 away, so you're actually a little farther out still. And over at pi, you're even farther away. And at 5 pi over 4, down here, you're even farther away still. So you see what this thing looks like. It's basically a spiral, okay? It's a spiral. And again, if you tried to, write an equation or some sort of relation in Cartesian coordinates to figure out what, to write an equation or some sort of relation to describe that thing in Cartesian coordinates, it would be a pretty complicated looking thing. But in polar coordinates, it's very, very simple, okay? So that's sort of the lesson here. When you're dealing in polar coordinates, anything with some sort of circular symmetry, like this isn't really symmetrical, but it varies as you go around the circle. It's sort of like symmetry. It's not exactly symmetrical, but as you sweep around the angles, you have very simple relations that can draw that graph. If you tried to draw that thing in Cartesian coordinates and write a function down, it would be much more complicated. So there's some very practical reasons why we like to use these things. So far we've had an introduction of polar equations and what they look like and roughly how you would graph a few of them. Now what we're going to do, analogous to the last section, is we're going to, if you're given a polar equation, a polar function, how would you convert that to the rectangular version of it? So if I had something that I had represented in polar coordinates, function, and I wanted to get the rectangular version of that function, what would I do? Okay, so for instance, let's say you had the polar function r times the sine of theta is equal to 2. Okay, r times the sine of theta is equal to 2. How would I convert that to rectangular coordinates? Well, remember from the last section we talked about this. The x-coordinate is just simply equal to r times cosine of theta, and the y-coordinate is equal to r times the sine of theta. That was derived in the last section, so that's sort of given to you here. Now all you have to do is use this information and plug it into here. Well, you see right away that r times the sine of theta is on the left-hand side of this equal sign in this function, and we know that that's equal to y. So all you have to do is say y is equal to 2, and that is the rectangular version. So it's a line, it's a horizontal line that goes on forever, okay? What if you were given, let's say, r is equal to 1 over 1 minus cosine of theta? How would you convert that to rectangular form? Well, first of all, let's get this denominator over here and let's have something prettier on the eyes to look at. So let's say you had r times 1 minus cosine of theta is equal to 1. Okay? R times 1 minus cosine theta is equal to 1. Now let's go ahead and distribute this r in. So it's going to be r minus r cosine of theta is equal to 1. I just distributed that in. And then again, we're going to recall that when we're trying to convert this guy back to rectangular coordinates, we're going to recall that r squared is equal to x squared plus y squared, right? So that means that r is equal to the square root of x squared plus y squared. Okay, that's just the definition of what r is, okay? So let's go ahead and do that here. Let's plug this in for r. We have r written right here. It's going to be square root of x squared plus y squared, okay, minus r cosine theta. Now I could go ahead and put this in here and multiply by cosine theta, but I also know that x is equal to r cosine of theta. That was given up here. It's just one of the equations that you learned in the last section to convert there. So any of those things, any of those conversion factors are in play here, and you can use any of them. So r cosine theta is a big red flag for me because I know that that's always equal to x. So I'm going to put x right here and say that's equal to 1. Now look here, I have x's and y's everywhere. I've gotten rid of all the r's and all the thetas. All that remains now is just to make it prettier. So I'm going to say x squared plus y squared is equal to 1 plus x, just moving the x over. And I'm going to square both sides. So I'm going to have x squared plus y squared is equal to 1 plus x squared. Okay, I'm going to square that guy here. And now I can just do FOIL on this. So it's going to be x squared plus y squared is equal to, first term squared is 1 plus 2 times a times b plus the last term squared. That's just FOIL. Okay, so I have x squared plus y squared is equal to x squared plus 2x plus 1. X squared plus 2x plus 1. Now notice I have an x squared on both sides here, so I can actually subtract x squared from both sides. It's basically going to cancel. Okay, those two things don't mean anything. I could subtract x squared from both sides and they would both disappear. So what I have in the end is y squared is equal to 2x plus 1. And I'm going to stop there. I mean, I could take the square root of both sides and have y is equal to the square root of 2x plus 1, but really it's the same thing. You're getting a rectangular expression, you're getting it as simple as you can, and whether or not you have a radical here or not is just up to you. And that's just the way you go. So basically, anytime you're given a polar equation, you plug in what you know for r. You plug in, if you see an r cosine theta or an r sine theta, it's usually a dead giveaway to just substitute for x and y, and then you just beat it into shape with the algebra. Now, just a minute ago, we did some problems where we were given a polar equation and we're trying to convert it to rectangular form. Now we're going to go backwards. What if you're given a rectangular equation and you want to convert it to polar form? How would you do that? So let's say your function was y is equal to 5, which as we all know is just a line that goes on and on forever horizontally at y is equal to 5 units up. There, it goes horizontal across. Now recall from the last chapter of this DVD that y is equal to r times the sine of theta. You should be having these guys memorized by now. And since you know this fact, you can just substitute in for y. So you can say r times the sine of theta is equal to 5. And you're done. You've done your conversion because all you're trying to do is take this function and take all of the x's and y's and make them into r's and thetas. And that's what you're trying to do, and that's what you did there. So that's it. And you could solve for r here, and you could plot that as a function of theta, and it would be exactly that. It would be a line. And if you wanted to be more explicit about it, you could just solve for r and say it's 5 over sine of theta, right? And that would be a form that you could sit there and plug in thetas as you go around the circle. You get different values of r, and you would find that it would actually be a horizontal line. It goes on forever, just as you know from the rectangular version. Now, what if I had a function? I think it should look familiar to you. X squared plus y squared is equal to 25. Well, you probably remember that this is the equation of a circle with radius 5, taking the square root, radius 5. So how would we transform that guy into polar representation and make sure we understand? Now remember from the previous section, you know that r squared is equal to x squared plus y squared. That was just one of the one of the conversion factors that we can use to convert coordinates. Well, look here, I have x squared plus y squared, and I have it here. So I know that on the left, this is equal to r squared is equal to 25. Okay? And I take the square root, r is equal to 5. And that's the answer. Now, we talked about the polar representation of a circle before. This is exactly that, circle with radius 5, because as you go around the circle, there's no explicit theta dependence. So no matter what angle you're at, the radius is always going to be equal to 5, and that's why it's a circle. Okay? So in this section, we have tackled the topic of equations in polar coordinates, or polar functions is another a way to say that. Okay? And they're really no different fundamentally than the functions that you're dealing with all your life in the rectangular world. Okay? Instead of y is equal to f of x, you have r is equal to a function of theta, f of theta. Okay? So as you go around the coordinate system in theta, you'll get different values of r, make your table, plot your function, and so on. And when you're converting back and forth between polar and rectangular, all you're really doing is using your conversion factors that we learned in the last section. X is equal to r cosine theta, y is equal to r sine theta, etc., and plugging them in appropriately and just trying to eliminate r and theta to get to rectangular coordinates, for example. And so with some practice, I think you'll get the hang of that. It's really not that terribly hard. You just need to really understand it because it is something that you'll need to use time and time again.
Learn anything at mathandscience.com.